Reality has a quiet habit of breaking our rules. We grow up thinking that bigger things are always heavier, that worlds are neat, solid marbles circling their stars in some tidy clockwork. Then we discover a planet so huge it could swallow thousands of Earths, yet so light it would bob on water like a toy. A world that forces us to admit that even our basic ideas about size, weight, and what a planet is can fall apart under the right conditions. In this video, we'll dive much deeper into this strange kind of planet and what it reveals about how little we really know. And if you enjoy learning like this while you drift off, a quick like on this video really helps other people find it too and get good sleep while learning. And I'd really appreciate a subscribe to show your support. Picture Jupiter for a moment, the biggest world in our whole solar system. A planet so large you could line up more than 1,000 Earths inside it and still have space left over. Now shrink Jupiter down in your mind until it is the size of a grapefruit sitting in your hand. Heavy, solid, familiar in a strange way. Next, imagine placing that grapefruit on a table beside a watermelon. That watermelon is this other planet, not a little bit bigger, not just slightly oversized. It completely dwarfs Jupiter. If Jupiter is already hard to grasp, this world stretches that sense of scale until it almost snaps. But here is the strange part. If you could somehow scoop this giant planet up and drop it into an unimaginably huge cosmic swimming pool, it would float, a world big enough to swallow Jupiter, bobbing like a beach ball on the surface. Bigger, but lighter. Enormous, but weirdly fluffy. It goes against the everyday rule your brain expects, that bigger things weigh more, that size and heaviness always go together. Jupiter feels like the final boss of planets in our solar system. For centuries, every time humans built a better telescope, we pointed it at that striped giant. We mapped its storms. We counted its moons. We watched lightning flash in its clouds. It became our mental template for what a gas giant is supposed to be. And then this distant world shows up and quietly says, actually, not always. Compared to this planet, Jupiter starts to look almost modest. A respectable giant, sure, but not the top of the scale. Our solar system's champion turns out to be just one example out of many, not the standard by which the universe must play. Think about what that means. For most of human history, big planet meant Jupiter. There was nothing else to compare it to. Our whole sense of what was reasonable for a planet was built around that one example. Then we begin to find worlds that break the pattern, worlds that stretch the idea of what a planet can be until the word itself starts to feel a little fragile. And this one is not sitting nearby where we could have easily found it earlier. It is more than 1,000 light years away. 1,000 years of travel, even for light, the fastest thing in the universe. The glow we see from its star tonight started its journey before telescopes were invented, before most of the ideas we use to understand the cosmos even existed. Out there, orbiting a star with a name most people will never hear, in a patch of sky most of us never think about, this huge, underweight planet just circles along. It does not announce itself. It does not shimmer in some special way. To the naked eye, its star is just another point of light among millions. We only know this world exists because we have started to look at those points of light differently. Not as distant decorations, but as suns, as places, as systems. Somewhere around this particular sun, this swollen, low-density planet races along its orbit, silently breaking our expectations. So we are left with a puzzle. How can a planet be that big, yet that light? How can something that makes Jupiter look small have less stuff packed inside it? What kind of physics allows a world to be so inflated that it would float like a toy in water? To answer those questions, we have to follow two threads at once. One is our history, how we went from knowing only the handful of worlds in our own sky to finding planets around distant stars. The other is the strange science of these swollen giants, planets that do not behave the way our simple mental picture of a planet says they should. Let's start with that history and see how we even learned to notice a world like this in the first place. To understand why this strange, oversized planet matters, we have to remember how small our view of the universe used to be. For most of human history, planet meant a few bright dots wandering slowly across the night sky: Mercury, Venus, Mars, Jupiter, Saturn. They did not twinkle like the other stars. They drifted, week by week, against the fixed background of constellations. To ancient eyes, they were omens, gods, signs. Signs. Nobody knew what they really were, only that they moved differently. Centuries passed, telescopes appeared. Our list of worlds grew, Uranus was added. Then Neptune, for a time, Pluto joined the club. But every one of these planets had something in common. They all circled the same star. Our star, our whole idea of a planetary system, was just this one, the home version. People wondered, of course, could other stars have their own families of planets? It felt almost arrogant to imagine that only our star had company. The universe is full of stars. If each one is a sun, why would ours be special enough to sit in the middle of the only set of worlds? So astronomers assumed other planets were out there, quietly, in their notebooks, in their conversations. It seemed like the reasonable guess. But there is a big gap between reasonable guess and we have proof. You can believe something is true for a long time and still have no way to show it. And proving it turned out to be incredibly hard. The basic problem is brutal. Stars are blindingly bright. Planets are tiny and dim. A planet does not shine on its own. It only reflects a little of its star's light, like a dust grain trying to glow in a floodlight. Imagine standing in Los Angeles on a dark night. Someone points toward New York and says, "See that lighthouse beam?" You squint, you pretend, but of course you cannot really see it. Now they add, "Okay, now look for a single firefly hovering right next to that beam." That is roughly the kind of problem astronomers face when they try to see a planet next to its star. The star is the lighthouse. The planet is the firefly, washed out by the glare. From our distance, the two are so close together in the sky that they blur into one point of light. The planet's reflected glow is billions of times fainter than the star. It is like trying to hear a whisper next to a jet engine. For a long time, that whisper was lost. Then, in 1992, something finally changed. Astronomers announced the first confirmed planets beyond our solar system, but the story came with a twist. These worlds were not circling a normal star like our own. Instead, they orbited a pulsar, the collapsed, rapidly spinning remnant of a star that had exploded. A pulsar is one of the strangest objects in the universe. Imagine a star's core crushed down until it is only a few dozen kilometers wide, yet still more massive than our star. It spins quickly, sweeping out beams of radiation. Like a cosmic lighthouse, we detect those beams as regular pulses. That is why we call it a pulsar. Finding planets around something like that is almost unsettling. A star dies in a violent explosion, and somehow, after all of that chaos, small worlds still circle what is left. It proved that planets can exist in places we would never expect. But at the same time, it raised another question. If you can find planets around a dead exotic star, what about normal, sun-like stars? Do they also have planets? Or were these pulsar planets just weird cosmic leftovers from a disaster? The real turning point came a few years later, in 1995. Two astronomers, Michael Mayer and Didier Queloz, announced that they had found a planet orbiting a star very similar to our own. The star was called 51 Pegasi, just another point of light in the constellation Pegasus, invisible to the naked eye for most people. Nothing about it screamed historic. The planet they found, though, was nothing like anything we had ever seen. It had a mass similar to Jupiter's, so it was clearly a gas giant. But unlike Jupiter, which takes almost 12 years to go around our star, this new planet whipped around its sun in just over 4 days. Not 4 months, not 4 weeks, 4 days. To do that, It had to be incredibly close to its star, so close that its year was shorter than a working week on Earth. So close that its atmosphere would be heated to temperatures of well over 1,000 degrees. A world the size of Jupiter, shoved right up next to its sun, racing around in a tight, blistering orbit. In our own solar system, the big gas giants live far out in the cold. Jupiter and Saturn sit beyond the asteroid belt, where icy material could pile up and form giant planets. Our picture of how planets form grew around that fact. Big gas giants live in the outer suburbs. Small, rocky planets live closer in. That was the rule. So when this first Jupiter-mass planet was found practically hugging its star, it felt wrong. Like finding a polar bear padding across sand dunes under a burning desert sun, it should not be there. And yet, it was real, measured in the data. The shock did not fade. More planets like it were found soon after. Huge gas giants, looping around their stars in a matter of days. They were given a new name: hot Jupiters. Not because they are rare, but because they were the first kind of planet our instruments could easily pick up. And that part is important. These planets did not show up first because the universe prefers them. They showed up first because the universe was willing to let us see them. A massive planet tucked very close to its star tugs strongly on that star. It makes the star wobble more obviously. It also blocks more of the star's light if it happens to pass in front of it from our point of view. In other words, a big, hot Jupiter right next to its sun leaves big fingerprints for our telescopes to notice. Those early detections taught us two things at once. First, planets around other stars really do exist. The old guess was right. Second, the universe does not feel obliged to follow the layout we are used to. Giant planets can lurk in places our theories once said they had no business being. And that opened the door to worlds even stranger, including one so swollen and light that it can make Jupiter look almost ordinary by comparison. Once astronomers had learned to spot those hot Jupiters hugging their stars, a simple pattern appeared. The bigger and closer the planet, the louder its presence. A massive world tugging tightly on its star makes that star wobble more. If the orbit happens to line up just right, that same planet will also block more of the star's light when it passes in front. In other words, a giant planet in a tight orbit does us an odd favor. It leaves big, obvious fingerprints on the light we see. Those fingerprints are what lead us to the largest planet in this story. The way we found it is based on an idea so simple, you could almost miss how powerful it is. Imagine you are looking at a street lamp from far away. The light seems steady and constant. Now imagine a tiny moth flies across the lamp's face. For a moment, the lamp is just a little dimmer. If your eyes were perfect, and you were very, very patient, you could notice that little blink every time the moth made a lap around the lamp. Replace the street lamp with a star. Replace the moth with a planet. If that planet's orbit happens to carry it directly between its star and us, then from our point of view, the planet will sometimes cross the star's face. While it does, it blocks a small fraction of the starlight. Not much. Just a tiny cut. But if you measure the brightness of that star carefully enough, over and over again, you see a little dip each time the planet passes in front. The star is shining along as usual. Then, very slightly, it dims. Then it returns to normal. Dip, flat. Dip, flat. A repeating heartbeat in the light curve. The depth of that dip tells you how big the planet is compared to the star. A small planet blocks a tiny fraction of the light. A big planet blocks more. The timing between dips tells you how long the planet takes to go around. Once, its year. The length of the dip tells you how long it takes to cross the star's face. All of that information is encoded in what looks, at first glance, like a small, boring wiggle in a brightness graph. This is the transit method. It is almost comically minimal. Stare at a star, wait for it to blink. But behind that simple idea is a quiet revolution in how we look at the sky. Instead of just asking, "Where is this star?" astronomers started asking, how steady is this star's light? Every star became not just a point in space, but a signal to be monitored. That is where a project with a slightly quirky name steps into the story. A hut. It sounds like something you put on your head, but here it stands for Hungarian-made automated telescope. Not one giant observatory on a mountain, but a whole network of small robotic telescopes spread around the world, built with one main job in mind: watch thousands upon thousands of stars, all night, every clear night, and wait for them to blink. The first of these telescopes started work in 2003 in Arizona. Nothing grand or towering. Each instrument has a lens only about 10 centimeters across. That is roughly 4 inches, comparable to what a serious amateur might have in their backyard. If you walked past one of these telescopes in the daytime, you might not guess it was helping to discover worlds. But that is the trick. You do not need a giant mirror to notice a star getting a few percent dimmer. You need patience. You need stability. You need a system that can stare at the same fields of sky night after night and measure tiny changes in brightness with almost obsessive consistency. So over time, the project grew. More telescopes were added in more places. Hawaii, Arizona, Namibia, in Africa, Chile, in South America, Australia, in the Southern Hemisphere. A loose ring of small robotic eyes around the globe. When the sky is bright in one place, it is dark in another. When dawn washes out the stars in Arizona, night has already fallen in Namibia. This means that together, the network can watch the same star for much longer stretches, catching transits that might otherwise slip past while one observatory sits in daylight or cloud. Each clear night, these instruments quietly gather data. They do not point at just one target. They sweep large patches of sky, tracking the brightness of hundreds of thousands of stars at once. To a human, the night is peaceful. To their cameras, it is frantic. Millions of brightness measurements, subtle flickers, slow drifts, all fed into software that searches for patterns. Somewhere in those patterns, between 2005 and 2005, and constellation of Hercules started to stand out. From Earth, Hercules is just a shape our minds draw in the stars, a set of points we connect into the rough outline of a mythic strongman. To the telescopes, one of those points was just a number in a long list. A star about 1,044 light-years away. Number 1 looking up with their naked eyes would ever pick it out as special. But in the data, it misbehaved in a very specific way. Every 4.81 days, the brightness of that star dropped. Not by a tiny fraction of a percent, not by some barely measurable amount, but by about 2.5%. Then it brightened again, and 5 days later, another dip. And again. And again. That might sound small, but in exoplanet terms, a 2.5% drop is huge. For comparison, if an alien civilization on a distant star were watching our star and saw Jupiter pass in front of it, the dip in brightness would be only about 1%. Jupiter, the colossus of our solar system, would barely nibble at our star's light. Whatever was crossing the face of this star in Hercules was blocking more than twice as much light as Jupiter would block in front of ours. That meant one thing: this object was big, not just big, enormous, relative to its star. But astronomy is full of tricks, illusions, and false alarms. Other things can mimic a planet transit, 2 stars eclipsing one another in the background, or a complicated binary system lined up just so. So the Haiti detection was not treated as a trophy immediately. It was treated as a clue. Years of follow-up work began. Larger telescopes turned toward Hercules to measure the star's motion, checking whether an orbiting planet was tugging on it. Observations at different wavelengths checked for signs that the dip was caused by something other than a planet. Astronomers tested every boring explanation they could think of. Could it be a faint companion star, an instrument glitch, a subtle error in the way the data were processed? One by one, the mundane options were crossed off. Only after this long, careful process After the original dips had been seen again and again, after the star's slight wobble matched the timing of the transits, did the team finally announce the discovery in 2017, a genuine planet transiting this distant F-type star in Hercules, and when they took its size and mass together and worked out its density, they realized they had found something that did not just join the list of known planets, it pushed the boundaries of that list. The dips in the starlight were not just telling them, there is a planet here. They were whispering something more unsettling. This planet is far larger and far lighter than you would ever expect. Let's pin this strange world down with some numbers before we let our imagination run away with it. Start with its path around its star. This planet orbits so close in that it completes a full loop in just 4.81 Earth days, not almost 5 weeks, not almost 5 months, less than your work week, and it has gone all the way around its sun. To pull that off, it has to sit at a distance of only about 7 million miles from its star. By comparison, Earth orbits at about 93 million miles. We live in the wide, cool suburbs. This planet lives right next to the furnace. The star itself is no gentle sun, either. It is hotter and brighter than our own, what astronomers call an F-type star. It has about 1.6 times the mass of our star, and roughly 1.85 times the diameter. A bigger, more intense version of our sun, pouring out more light and more energy. Put a planet that close to a star like that, and you get temperatures that sound almost made up. The balanced temperature of this world, the rough temperature it settles at from starlight alone, is around 1900 Kelvin. On the scale most of us use, that is about 1620 degrees Celsius, or roughly 2960 degrees Fahrenheit. That is hot enough to melt most metals. Hot enough that the planet does not just reflect light, it glows from its own heat, like a piece of metal pulled out of a forge. This world is not just warm, it is being cooked, constantly. Now, zoom out in your mind and look at its size. Jupiter, our local giant, is about 88,000 miles across at its equator. Imagine stretching a tape measure from one side of Jupiter to the other. Now keep pulling until that line is more than doubled. This distant planet spans almost 185,000 miles from side to side. Across that diameter, you could line up about 23 Earths in a row, each touching the next. If you hollowed the planet out and tried to pack Earths inside like marbles in a jar, you could fit around 12,000 of them by volume. Among all the confirmed exoplanets we have measured, this one sits at the top of the list by size. In terms of radius, it is the current record holder. You might expect a world that large to be a real heavyweight. Bigger planet, more stuff, more mass. That is the rule we are used to. But this is where the universe decides to break the rule. Despite being more than twice Jupiter's size, this world has less than half of Jupiter's mass. The best measurements put it at about 0.45 times Jupiter's mass. So picture two spheres. One is Jupiter, smaller but heavy. The other is this world, much larger, but containing less material overall. Stretch the same amount of stuff out over a much larger volume, and it gets thin, fluffy. The average density of this planet works out to about 0.06 grams per cubic centimeter. Water sits at 1 gram per cubic centimeter. That is the reference point. Most of the rocks and metals you know are several times denser than that. Even Saturn, the least dense planet in our solar system, is about 0.7. This world is around 1/16 the density of water. If you could somehow build an ocean large enough to hold it, this planet would float. Not just bob at the surface, but float easily, like a giant beach ball. So here is the picture so far, a planet that is more than twice the diameter of Jupiter, big enough to swallow thousands of Earths. So light, on average, that it would float in water, racing around a star bigger and hotter than our sun in less than 5 days, heated to temperatures that melt metals and make it glow by its own heat. Huge, underweight, scalding, and very, very close to its star. All of that packed into one world, so now we run into the real puzzle. How can a planet be so enormous and yet so light? How can something that would dwarf Jupiter be fluffier than a beach ball? To see why this is so strange, it helps to think about what a giant planet is made of in the first place. Take Jupiter. Our local giant is mostly hydrogen and helium. Those are the lightest elements in the universe. In fact, roughly 9 out of every 10 atoms of Jupiter's mass are hydrogen. You might imagine that would make Jupiter a very low-density world. But deep inside, the rules change. As you go down into Jupiter, the pressure climbs to incredible levels. The gas is squeezed by the weight of everything above it. Under that crushing pressure, hydrogen stops behaving like the familiar gas we know from balloons. Near Jupiter's center, the hydrogen is pressed so tightly together that it becomes metallic. That doesn't mean it turns into a shiny bar you can hold, but it does start to act like a metal in one important way. It can conduct electricity. It is still made of the lightest atom in the universe, but the pressure has forced those atoms into a dense, exotic state. This distant giant is also made mostly of hydrogen and helium. The ingredients are not exotic. What's exotic is how those ingredients are arranged. Instead of being squeezed into a relatively compact ball like Jupiter, this planet is puffed out. Imagine taking a normal marshmallow and putting it in a microwave for a few seconds. It swells. The amount of sugar inside doesn't change, but it spreads out into a bigger, softer shape. The same idea applies here. The material is spread over a much larger volume, so on average, it is incredibly thin and light. The star is doing the microwaving. When you heat a gas, it expands. That is one of the simplest ideas in physics. Warm air takes up more space than cold air. The molecules move faster. They bump into each other more. They push outward harder. On Earth, this is why hot air balloons rise. Heat the air inside the balloon. It becomes less dense than the air around it, and the balloon floats upward. Now imagine that concept on the scale of a planet. This world orbits so close to its star that its upper atmosphere is constantly blasted by intense radiation, day after day, year after year, for billions of years. Light from the star pours energy into the gas at the top of the planet. That energy makes the gas expand. The outer layers puff up, and the whole planet becomes swollen compared to a cooler cousin like Jupiter. That's the simple picture. Hot star, hot atmosphere, puffed up planet. But when scientists plug all of this into detailed models and do the math, something uncomfortable happens. Just heating the outer layers does not seem to be enough to explain how extremely puffy this particular planet is. The observed size is even larger than what the basic hot air balloon effect should produce, so something else must be helping to blow it up. One possible source of extra heat comes from the planet's orbit. If its path around the star is not a perfect circle, but slightly stretched into an oval, then its distance from the star changes during each orbit. Closer in, the star's gravity pulls more strongly. Farther out, the pull is weaker. That constant squeezing and relaxing can flex the planet slightly, kneading it like dough. Whenever you repeatedly bend or stretch something, you generate heat through friction. You can feel this with a paperclip in your own hands. Bend it back and forth enough times and it gets warm. In a planet, that tidal flexing could create heat deep inside, slowly pumping extra energy into the interior over billions of years and helping to keep the planet bloated. Another idea involves the planet's magnetic field. Gas giants often have powerful magnetic fields, like Jupiter's enormous magnetic bubble. The star, meanwhile, blows out a stream of charged particles called the stellar wind. If you have a magnetic field and a flow of charged particles interacting with it, you can generate electrical currents. Those currents can run through the planet's upper atmosphere, and as they meet resistance, they turn electrical energy into heat. That heat can then leak downwards, warming the planet from within. There is also the possibility that the planet's own atmosphere acts like a very effective blanket. Certain layers of gas might be especially good at trapping heat, preventing it from escaping into space. If the heat leaks out only slowly, the interior stays warmer for longer. A hot interior means more expansion, more puffiness, and a lower density overall. Right now, the honest position is simple and refreshing. We do not fully know. We have several ideas that probably all play some part: stellar heating, tidal flexing, magnetic effects, heat-trapping layers, but we do not yet have a single, neat explanation that ties everything together. This planet is so extreme that our usual models struggle to catch up to it. That is exactly what makes it valuable. It is not just a curiosity. It is a kind of laboratory in space. A test case that forces our theories of giant planets to either work under harsh conditions or be rewritten. The environment on this world is as extreme as its structure. At such a close distance to its star, the planet is almost certainly tidally locked. We see this effect in our own sky with the moon. The moon always shows us the same face because over time, Earth's gravity slowed and synchronized its rotation. One side of the moon is forever turned toward us, the other forever turned away. For this planet, the same thing likely happens with its star. One hemisphere always faces the star, baked in perpetual daylight. The other hemisphere always faces away, sunk in endless night. That creates a world split in two. On the day side, the planet's face is constantly hammered by radiation. Temperatures climb to thousands of degrees. On the night side, there is no direct starlight at all. Left alone, it would be much cooler. But the planet has an atmosphere, and atmospheres do not just sit still. Hot gas on the day side expands and tries to flow toward cooler regions. Cooler gas on the night side sinks and tries to move toward the heat. This sets up powerful winds that rush from day to night and back again. Along the dividing line between the two halves, the region astronomers call the terminator, there would be a band of eternal twilight with screaming winds racing across it, possibly at thousands of miles per hour. Picture an entire planet wrapped in a churning, high-speed river of gas, driven by the brutal temperature difference between everlasting day and everlasting night. And whatever you imagine when you hear the word atmosphere, this is not that. There is no breathable air here, no oxygen worth mentioning, no blue sky. The main ingredients are almost certainly hydrogen and helium, the same light gases that make up the bulk of the planet itself. At the temperatures we are talking about, chemistry becomes strange. Substances that we think of as solid or liquid on Earth can exist as gases in the air. Compounds like titanium oxide and vanadium oxide, things we use in pigments and industrial processes, might float high in the atmosphere as hot vapors, absorbing starlight and heating the upper layers even more. Go hotter still. And even metals can turn to mist. Some scientists think that in worlds like this, iron and magnesium may exist as vapor in the atmosphere on the scorching day side. Iron, the stuff of nails and skyscrapers, reduced to a gas. As that superheated metal vapor drifts into slightly cooler regions, it could condense into tiny droplets and fall, like metallic rain, down through the deeper atmosphere. Rock itself may be part of the weather. On Earth, silicates are the materials of stone, granite, sand, glass. Here, that same kind of material could be vaporized on the hottest dayside regions, then condense into fine dust higher up, forming clouds of rock. Imagine clouds made of powdered stone, carried around the planet on winds blowing faster than the speed of sound. We do not know exactly what this world looks like to the eye, but we can guess at possibilities. Depending on which chemicals are present and how they absorb and reflect light, the planet might be almost pitch black, soaking up most of the starlight that hits it, or it might glow with eerie colors, its hot gases emitting their own light, painting the atmosphere with shades we do not really have names for. We cannot yet take a sharp, direct photograph of the planet's surface and settle the question. All we have are patterns of light and carefully built models, plus observations of similar worlds. So we live in this halfway place between knowledge and imagination, anchored by numbers, but still filled with pictures we have to construct in our minds. And in that halfway place, This planet sits as a kind of challenge, a reminder that even when we know roughly what something is made of, we can still be surprised by what those simple ingredients can do under the right extreme conditions. Finding this planet and pinning down its size, its mass, its orbit, and temperature was really just a first layer. It's like noticing the outline of a distant city on the horizon. You know it's there. You know roughly how big it is, but you still have no idea what the streets look like, what the air smells like, what lives there. For a planet, the air is where a lot of the interesting physics hides. The atmosphere is the layer that talks to the star, that absorbs light and heat, that moves and circulates and reacts. If we want to do more than just say, there's a giant, fluffy planet over there, we have to find a way to read the story written in its gases, and surprisingly, with nothing but light, we can. Think back to that transit again. The planet passes in front of its star, and for a short while the star's brightness dips. Most of the star's light is blocked by the solid bulk of the planet, but a thin ring of atmosphere around the edge is still partly transparent. Some of the starlight skims through that ring on its way to us. As that light passes through the gases, atoms and molecules in the atmosphere interact with it. They don't just dim it randomly, they are very picky. Each kind of molecule prefers certain colors of light and ignores others. It is a bit like having thousands of tiny stained glass windows, each one removing only a very specific shade. If you take that light and spread it out into a rainbow, what scientists call a spectrum, you no longer see a smooth band of colors. You see a rainbow with little bites taken out of it. Thin, dark lines or dips where certain wavelengths are missing. Those missing colors are the fingerprints of the gases that absorb them. This is the basic idea of transmission spectroscopy. Watch the star while the planet is not in front of it. Record the spectrum of its light. Then watch again during a transit and record the spectrum once more. Compare the two. The tiny differences between them reveal which wavelengths were absorbed by the planet's atmosphere, and therefore which gases are there. It sounds almost like a magic trick. We can tell what the air is like on a world 1,000 light-years away by the way its star's rainbow is slightly bruised during a blink. But it is just careful physics, repeated many times. Using this technique, astronomers have already detected things like water vapor, sodium, potassium, and other molecules in the atmospheres of several exoplanets. Not as big, sweeping images, but as subtle patterns in graphs. Little dips at very precise colors that say, water was here, or sodium passed by. Now think about our swollen giant and what makes it special in this context. Because its atmosphere is so puffed up, that thin ring around the edge is not really thin. There is a lot of gas for the starlight to travel through. The more atmosphere you have, the more chances there are for photons to get absorbed at those characteristic wavelengths. That means the fingerprints in the spectrum are easier to see. If you are trying to identify a smell in a room, it is much easier if someone has spilled an entire bottle of perfume than if they sprayed a single tiny drop. This planet, atmospherically speaking, is the entire bottle. That is why worlds like this are such tempting targets. Their very weirdness, their bloated, low-density envelopes, gives us a clearer laboratory to work with. We can test our techniques, refine our models, and see how atmospheres behave under extreme heating. And now we have a tool in space that is almost perfectly built for this kind of work. The James Webb Space Telescope sits far beyond the reach of Earth's atmosphere, which means it does not have to fight our own air to see delicate details in starlight. It is incredibly sensitive to infrared light, the kind of light where warm objects glow, and where many important molecular fingerprints light. When Webb turns toward a system like this, it can watch multiple transits, measure the tiny changes in the star's spectrum during each one, and build up a detailed picture of the planet's atmosphere. What gases are there, how hot the different layers are, maybe even hints of how heat moves from dayside to nightside. Every bit of information we pull from this single inflated world feeds into a bigger picture. Hot Jupiters like this one sit at the edge of what planetary physics can handle. They are pushed to limits of temperature, radiation and structure that our theories were not originally built to describe. By studying them, we are not just ticking off another entry in a catalogue, we are stress testing our understanding of how planets work at all. If our ideas about atmospheres, heat flow, gravity and gas behavior can explain worlds like this, they are probably on the right track. If not, we have to adjust them. And once we refine those ideas on these extreme giants, we can carry the improved understanding back to calmer places, to cooler gas giants, to ice giants, and eventually to small rocky planets where the question is not, why is it so puffy? But could something live under that sky? When you hear all these numbers, it can help to anchor them to something familiar. So let's start at home, with the giant we actually know. Jupiter is the heavyweight of our solar system. It's so massive that if you piled up all the other planets, Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, Jupiter would still outweigh the entire set. If you could magically scoop out its insides and use it as a shell, you could pack about 1,300 Earths into that hollow space. It's not just big, it's busy. At least 95 known moons orbit Jupiter. Some are worlds in their own right. It hosts the Great Red Spot, a storm larger than our planet, that has been swirling for centuries without stopping. When you look at Jupiter, you're seeing a piece of physics running in slow motion on a ridiculous scale. Now place this distant world beside it. This record planet is more than twice Jupiter's diameter. Imagine Jupiter as a sphere, and then imagine another sphere so large you could tuck about 9 Jupiters inside it by volume. That's the scale difference we're talking about. Our solar system's giant suddenly looks like the medium size on the menu, and still, this is not the only bloated world we've found. Take WSP 79b, another inflated hot Jupiter, orbiting a star about 790 light-years away. It's big, around 2 times Jupiter's radius. For a long time, that kind of size seemed outrageous. For a long time, that kind of size seemed outrageous. But even that impressive world is still a bit smaller than the one we're focusing on. Or WASP 17b, discovered in 2009. For a time, it wore the crown as the largest known exoplanet. Its diameter is about 1.89 times that of Jupiter. Again, enormous, and again, now overtaken. Then there's KELT, then there's KELT 9b, one of the hottest exoplanets we know. Its dayside temperature climbs above 7,800 degrees Fahrenheit, hotter than the surface of some stars. It's about 1.9 times Jupiter's diameter. Wildly extreme, but still not quite as large as this puffed-up planet we're talking about tonight. You might ask, if we keep finding bigger and stranger worlds, where does planet end? At what point are we just looking at a baby star? That's where brown dwarfs come in. They sit in the awkward middle ground between planets and stars, too small to sustain steady hydrogen fusion in their cores, like true stars do, but too massive to be considered planets. Typically, they're at least 13 times Jupiter's mass. Some are puffy and large in radius, and from far away they might look like giant planets. But they're not planets, they're failed stars. This record-breaking world does not fall into that grey zone. With a mass of only about 0.45 Jupiter masses, it's nowhere near heavy enough to count as a brown dwarf. There's no chance of it igniting hydrogen in its core. It is firmly on the planet side of the line. What makes it remarkable is not that it's secretly star-like, but that it's so inflated for its modest mass. That leads to a natural question. How big can a planet actually get? There is a limit, and it's set by the tug-of-war between gravity and the material inside. As you add more mass to a gas giant, its gravity gets stronger. You might expect it to swell like a balloon. But that's not what really happens. Extra gravity squeezes the gas harder, increasing the density. Past a certain point, Adding more mass does not make the planet much bigger, it just makes it more compact. Jupiter is already close to this natural maximum size for a cold gas giant, made mostly of hydrogen and helium. If you kept pouring more gas onto Jupiter, it wouldn't balloon to twice its diameter. It would likely stay roughly the same size and just get heavier and denser. So when we see planets that are clearly larger than Jupiter, something unusual is going on. They're not huge because they have vastly more material. They're huge because some process has puffed them up, spreading that material out into a larger volume. In this planet's case, the culprit is its environment. Take away the intense radiation from its nearby star. Move it out into the cold dark where Jupiter lives. Give it billions of years to cool and contract. Over time, it would shrink down, likely ending up roughly Jupiter-sized, maybe even smaller. The giant we see now is not its natural resting state. It's a body held in an artificially inflated condition by the energy constantly pumped into it. That's why worlds like this are so interesting. They show us that a planet is not just a fixed object with a fixed size. The same amount of matter can look very different depending on where it lives and what it's been through. External conditions, heat from the star, orbital history, internal energy can reshape a planet's structure in dramatic ways. And this particular planet's story doesn't stop with its shape and size, because when you look at how close it orbits today, at only about 7 million miles from its star, another mystery appears. There's almost no way it could have formed right where we find it now. If you rewind this planet's story back to its beginning, its current orbit makes no sense at all. At about 7 million miles from its star, the space around it would once have been far too hot for ices to exist. In the early days of a planetary system, you need ice and rock to build a solid core quickly. That core then becomes the seed that pulls in gas and grows into a giant planet. Close to a young hot star, those ices just can't form. There isn't enough solid material there to build a massive core in time. So a gas giant like this should not have been able to assemble itself where we find it now. And yet, there it is, very much real, looping around its star in an orbit that looks forbidden on paper. The simplest way to resolve this is to accept that the planet probably didn't start there. Most likely, it was born much farther out, in the colder regions of the system where ices could form and clump together. Out there, a solid core could grow quickly, then pull in vast amounts of hydrogen and helium from the surrounding gas disk. Only after it had become a true giant would it have begun the slow inward journey to where we see it today. That journey almost certainly happened while the system was still young and filled with gas. Picture a newly formed planet orbiting inside a wide, flat disk of gas and dust around its star. As it circles, its gravity pulls on the gas, and the gas pulls back. This tug of war doesn't happen evenly. The planet stirs up spiral waves in the disk, regions where the gas is slightly denser or thinner. Those spirals act like cosmic brakes. They steal a bit of the planet's orbital energy and angular momentum. Losing angular momentum is the key. In orbit, that's what keeps you far from the star. Take it away, and the orbit shrinks. Very slowly, over millions of years, the planet spirals inward, moving from the cold outskirts into a much tighter, hotter orbit. This process has a name, type I-2 migration, and it's probably common. Many hot Jupiters may have been born in the distant chill and then gently dragged inward by their birth disk. But the details can differ wildly. Some planets may plunge quickly toward their stars and park themselves in orbits of just a few days. Others may drift more slowly or stall partway through. Under some conditions, the interaction with the disk might even push a planet outward instead. And the disk isn't the only sculptor. If there are other planets in the system, and we strongly suspect many stars host multiple worlds, then their gravity can complicate the picture. Giant planets can nudge one another into new paths. A distant, unseen planet could have pulled on this one over time, stretching its orbit into a more elongated shape boosting the tidal heating we talked about earlier. Or a chain of planets might have passed angular momentum between them, helping to shove this world inward into its current roasting track. We don't know yet how crowded this system really is. It may be just this giant, or there may be smaller companions we haven't noticed, tugging silently, leaving only tiny timing shifts in its orbit as clues. Future observations may pick up those hints, small variations in when the planet transits, subtle shifts in its motion. If they do, we'll discover that this single planet story is actually part of a more intricate dance. Even now, the planet lives in a kind of danger zone. Hot Jupiters like this orbit so close to their stars that they are constantly exposed to intense radiation. High-energy light and charged particles slam into their upper atmospheres and can knock atoms and molecules free. Over time, gas can escape the planet's grip and drift off into space. Some worlds show actual comet-like tails of gas streaming behind them, evidence that their atmospheres are slowly being stripped away. This planet's extremely low density makes it especially vulnerable. Its mass is spread out over such a huge volume that its surface gravity is relatively weak for a gas giant. The escape velocity, the speed a molecule needs to reach to break free, is lower than it would be on a more compact world. That means it is easier for high-energy particles and photons from the star to kick bits of its atmosphere into space and keep them there. But vulnerable does not mean doomed tomorrow. There are planets even closer to their stars than this one, racing around in orbits shorter than a single Earth day. Those ultra-hot Jupiters endure even more brutal conditions, and many of them are actively evaporating in dramatic fashion. Compared to them, a nearly 5-day orbit gives this giant a little breathing room. It is still being eroded, most likely, but not in an immediate, catastrophic way. The star's own life story sets the final limit. F-type stars burn brighter than our sun and live faster lives. They spend their hydrogen fuel more quickly, so their stable phase lasts fewer billions of years. This particular star is thought to be around 3 billion years old, roughly middle-aged for its type, with several billion years of relatively steady burning still ahead. But eventually, its core will run low on hydrogen. When that happens, the star will swell into a red giant. Its outer layers will expand outward, and the inner planetary system will be engulfed. Any planets hugging close to the star, no matter how large they are, will be swallowed. Their orbits will decay inside the bloated star, and they will be dismantled and digested by the very object they once orbited. This is not a unique tragedy. It is the standard ending for many planetary systems. Our own sun will go through a similar transformation in about 5 billion years. When it becomes a red giant, Mercury and Venus will almost certainly be consumed. Earth may be, too, if not physically swallowed, then scorched beyond recognition. Every planetary system carries a built-in expiration date, written in the fuel supply of its star. Right now, this giant world exists in a kind of temporary balance. It has survived its migration inward. It endures the constant cooking of its star. It is slowly losing some of its atmosphere, but still holds on to its swollen form. A billion years from now, it may be smaller, denser, stripped down. 2 billion years from now, it may be gone entirely, erased by the expanding star that gave it light. We happen to live in the thin slice of time when this planet both exists and can be seen by us. Our telescopes catch its shadow, our instruments measure its wobble. Our minds get to wrestle with what such a world means. On cosmic timescales, that is a brief moment. But it is enough. The distance to this world is one of those numbers that look simple written down and almost meaningless when you try to feel it. On paper, it's about 1,044 light-years away. That means the distance light travels in 1,044 years. And light is fast in a way our brains are not built for. It moves at about 186,000 miles every second. In the time it takes you to blink, light could race around Earth several times. It can go from Earth to the Moon in a little over a second. Even at that speed, the gap between stars is so large that light has to crawl, 1 year at a time. Light from our own star takes just over 8 minutes to reach us. When you look at the sun, through proper protection, hopefully, you are seeing it as it was 8 minutes ago. Light from the nearest star beyond our solar system, Proxima Centauri, takes about 4.25 years to get here. If that star suddenly vanished, we would keep seeing its light for more than 4 years before reality caught up to us. Now stretch that out to over 1,000 years. When we look at the star hosting this giant planet, we are not seeing it as it is now. We are seeing it as it was around the year 1000 on Earth. That light left when there were no telescopes, no modern science, no electricity, no planes. The Norman conquest of England hadn't happened yet. The great universities of Europe did not exist. The Crusades had not begun. While knights and farmers and traders walked under our sky, that star's light began its journey toward us. It has been traveling, uninterrupted, across empty space ever since, and only now is it arriving in our telescopes. So every time we study this system, we are looking 1,000 years into the past. The planet we measure is the planet as it was then. If something dramatic happened to it yesterday, if its atmosphere changed suddenly, or its orbit shifted, we will not see that for another 1,000 years. The universe has a built-in delay. The distances involved also mean something a bit sobering. Isolation. Even if we could somehow travel at the speed of light, which our current understanding of physics says is impossible for anything with mass, a trip there would still take more than 1,000 years, one way. No human mission, no probe, no quick visit is realistically imaginable. The fastest spacecraft we have ever launched, Voyager 1, plods along at about 17 kilometers per second, or roughly 38,000 miles per hour. At that speed, the journey to this star system would take more than 11 million years. That's longer than our species has existed in anything like its modern form. So when we talk about this planet, we are talking about a place we will never visit, never sample, never photograph up close. Not just not in our lifetimes, but not in any human lifetime at all. It is beyond our reach in a way that feels almost absolute. And yet, somehow, we know quite a lot about it. We know its size. We know its mass. We know how long it takes to go around its star. We have a good estimate of the temperature in its atmosphere. We are beginning to tease out hints of what that atmosphere is made of, all from a whisper of light that has crossed 1,000 years of space. That is the part that deserves some quiet awe. We are tiny creatures clinging to a small rocky planet, and yet we have learned to read the universe from a distance. You might wonder how astronomers can be so confident. How can we say, with a straight face, that a planet we will never see directly is about 2.1 times Jupiter's diameter and about 0.45 times its mass? How can we talk about its density as if we had held it in our hands? The answer lies in the way different methods cross-check each other. The size comes from the transit method, and at its core, that method is just geometry. When the planet passes in front of its star, it blocks a certain fraction of the star's light. The fraction depends on the ratio of their areas. A planet that is 1/10 the star's diameter blocks 1% of its light. A planet that is bigger blocks more. So we watch the star's brightness dip during a transit and measure how deep that dip is. That tells us how big the planet's disk is compared to the star's disk. To turn that ratio into an actual size, we need to know how big the star is. That might sound like guesswork, but it isn't. Stars are not random. They follow well-tested relationships between their temperature, their brightness, and their size. By studying the star's light, how hot it appears, what elements show up in its spectrum, and knowing how far away it is, we can work out how luminous it truly is, and from that, what its radius must be. Those ideas have been tested for over a century, on stars in many different contexts. We've cross-checked them with binary stars, where two stars orbit each other, and their sizes can be inferred from their motions and eclipses. We've used a technique called parallax, watching how a star's apparent position shifts as Earth orbits, to measure distances directly. We've even studied tiny vibrations in stars, starquakes, to estimate their internal structure and size. All of this consistency gives us confidence. This star is about 1.85 times the diameter of our Sun. Once you know the star's size, the transit depth tells you the planet's size. It's like holding a ball in front of a lamp and measuring how much of the lamp's face the ball covers. The math is simple, and we've applied it to many other systems where independent measurements agree with the results. The mass comes from a completely different line of evidence. The star's wobble. As the planet orbits, it doesn't just circle the star while the star sits still. They both orbit a common center of mass. The star's motion is small, but it's there. As the star moves toward us and away from us in this tiny dance, the wavelengths of its light shift, slightly bluer when it moves toward us, redder when it moves away. This is the Doppler effect, the same principle that makes a siren change pitch as it passes you. By measuring that subtle shifting pattern in the star's spectrum, astronomers can work out how fast the star is moving toward and away from us. The strength of that wobble depends on how massive the planet is and how close it is to the star. Because the transit has already told us the orbital period and geometric setup, we can plug in the numbers and solve for the planet's mass. These two methods, transits and radial velocity, are independent. One gives the radius, the other gives the mass. Combine them, and you get the density. In this case, both sets of measurements line up neatly, each reinforcing the other. The orbital period from the brightness dips matches the period from the wobble. The size and mass fit together into a picture of a very low-density gas giant. On top of that, these techniques have been stress-tested elsewhere. We've applied them to systems where we can also use other tools like direct imaging. We've checked our stellar size estimates with asteroseismology by studying the ripples and vibrations in stars. We've compared masses derived from Doppler shifts to masses in binary systems where gravity's pull can be measured directly. Again and again, the methods hold up. So even though this planet is too far away to ever visit, even though its light left when human history looked completely different, our picture of it is not a hazy guess. It's the result of multiple lines of evidence, all converging on the same strange conclusion. Yes, this world really is that big. Yes, it really is that light. Yes, it really is out there, circling a star 1,000 years away in time as well as space. We have already learned a lot from this swollen giant, but in many ways, we are still only scratching the surface. The real treasure is in its atmosphere, and we are just now getting tools sharp enough to carve out the details. When the planet passes in front of its star, we do not just see a dip in brightness. Some of the starlight threads its way through the thin shell of gas around the planet's edge before it reaches us. On its way through, that light is changed. Different gases in the atmosphere soak up different colors, very selectively. Water vapor prefers certain wavelengths. Carbon dioxide prefers others. Methane has its own set. Sodium, potassium, titanium oxide, vanadium oxide. Each one leaves its own pattern in the light. If we spread the starlight out into a spectrum during a transit and examine it carefully, we can see tiny scars where those colors are missing. Those scars are like barcodes. By matching them to the fingerprints of known molecules, we can start to list what is floating in the planet's air. Not from a sample in a bottle, just from the way the star's light has been edited on its way past. That is what the James Webb Space Telescope is so good at. It stares through space with extremely sensitive eyes, especially in infrared light, where many of these molecular fingerprints are strongest. When it watches a transit of a world like this one, it can pick out subtle shifts in the spectrum that older telescopes would have missed. From that, we can build more than just a shopping list of molecules. Different layers of the atmosphere absorb and emit light at different wavelengths. If you see how the spectrum changes across many colors, you can reconstruct how temperature changes with height. Hotter here, cooler there, warmer again deeper down. A vertical temperature profile, drawn from nothing but light, shows how energy flows through the atmosphere. It tells us whether heat from the star is trapped high up or carried deep inward. It shows where energy escapes back into space and where it lingers. In time, we might even catch hints of weather. If this planet has massive storms or bands and spots like Jupiter's Great Red Spot, they will not line up the same way in every transit. Different parts of the atmosphere will pass in front of the star at different times. That can cause tiny changes in the shape of the dimming curve from one transit to the next. One pass might show a slightly deeper dip at a certain moment, another a slight bump somewhere else. Those differences could reveal patterns in the clouds, temperature contrasts, or giant structures in the atmosphere. From our perspective, it would be like watching shadows shift across a distant lamp and inferring the presence of storms on a world we can never see directly. Ground-based telescopes, even though they look through Earth's own atmosphere, still have a role to play. With very high-resolution spectrographs, they can split light into extremely fine color slices. That precision allows them to detect the faint signatures of molecules in the planet's air, even when those signatures are subtle. They can also measure tiny shifts in those molecular lines as the gas moves toward or away from us. Those shifts tell us about wind. If the atmosphere is racing from the hot day side to the cooler night side, gases on one limb of the planet may be moving toward us, while gases on the other limb move away. Measured carefully, these motions show up as small Doppler shifts in the spectral lines. From this, we can estimate wind speeds and directions, mapping flows in the atmosphere of a world more than 1,000 light-years away. Meanwhile, astronomers will keep watching the timing of the transits themselves. Most planetary systems we know about have more than one world. Our own has 8. Other systems we've found sometimes have 5, 6, or even more planets. If there are additional planets around this star, they might betray themselves in a few ways. They could produce their own transits, small extra dips in the starlight at different intervals. Or they could tug gently on the giant, causing its transits to happen a little earlier or a little later than expected. Even moons are not out of the question. A large moon orbiting this huge planet would have its own gravity, its own orbit. Sometimes it might pass in front of the star slightly before or after the planet, carving a smaller notch into the light curve. Sometimes it might slightly change the timing or duration of the main transit. Detecting such an exomoon would be difficult, but it would be an entirely new kind of discovery. A moon around a world like this would open up a new chapter in the study of other systems. So far, despite careful searches, we have not confirmed any exomoons anywhere. If we ever do, it may well be in systems like this one, where the transits are deep, the signal is strong, and the world has been on our watch list for a long time. All of this reminds us that the story is not finished. Each new observation tightens the picture just a little. Each new measurement rules out some possibilities and highlights others. Since this planet was first announced, astronomers have spent years revisiting it with different instruments, and they will keep doing so for decades. New telescopes will come online. New techniques will be invented. The same world will keep revealing new layers. One of those future tools is being built in Chile, the European Extremely Large Telescope. Its main mirror will be almost 40 meters across, big enough to gather staggering amounts of light. With that, it will be able to directly image some exoplanets orbiting nearby stars, separating their faint glow from the glare of their suns. It will also dissect their light with high precision, studying their atmospheres in more detail than ever before. In space, the Nancy Grace Roman Space Telescope will launch with a different mission. It will use a method called gravitational microlensing to find planets. When a star passes in front of another, its gravity bends and magnifies the light of the background star. If a planet is orbiting the foreground star, it can add an extra blip to that magnification. This technique is especially good at finding planets far from their stars, in regions where other methods struggle. Roman will fill in parts of the planetary census that are currently almost blank, so a world first discovered by a network of small, relatively modest ground-based telescopes will end up being examined by some of the most powerful machines our species has ever built. That is how science tends to work. One tool opens the door, others follow and explore the hallway. Each step builds on the last. Questions lead to answers, and answers lead to better questions. If we zoom all the way out from this one bloated giant and look at the bigger picture, the change over a single human lifetime is astonishing. Before 1995, the number of confirmed planets beyond our own solar system was exactly 0. We had stories, theories, hopes, but nothing you could point to and say, here are the measurements, here is the orbit. Here is the Borte. Here is the mass. In terms of hard evidence, we were alone. Now, only a few decades later, we have confirmed thousands of exoplanets. More than 5,700 and counting, with thousands more likely waiting in the data, not yet fully checked and confirmed. In that growing catalogue are almost every kind of world you can imagine, and many that you would never think to invent. Rocky planets smaller than Earth. Gas giants larger than Jupiter. Planets that skim so close to their stars that they are tidally locked and half-molten. Planets that take only a few hours to complete an orbit, racing around their suns in a cosmic sprint. Others that creep along in vast loops that might take centuries to finish. We found planets in the habitable zones of their stars, where temperatures could allow liquid water to exist on a surface. Not proof of life, but the basic condition that life as we know it seems to require. We found planets circling 2 stars at once, with double sunsets and double dawns. We found worlds so close to their stars that their surfaces are probably oceans of lava, and we found rogue planets not bound to any star at all, drifting alone through interstellar space in deep darkness. Put all that together, and one big lesson emerges. Planetary systems are not rare. They are the norm. Almost every star you see when you look up is probably surrounded by at least one planet, and often more. The Milky Way contains on the order of hundreds of billions of stars. If most of them host planets, we are talking about hundreds of billions of worlds in our galaxy alone, and our galaxy is just one out of at least a couple of trillion galaxies in the observable universe. The total number of planets out there is a number so huge that it stops being a number and becomes more like a feeling. A kind of cognitive vertigo. Somewhere among all of those worlds, there may be life. This is one of the deepest motivations behind exoplanet research. We want to find Earth-like planets, rocky, roughly our size, sitting in the gentle zone around their stars, where liquid water can exist on their surfaces. Not because that guarantees life, but because it makes life, at least as we understand it, physically possible. This giant planet is not a candidate for life. It has no solid surface to stand on. Its temperature would tear apart complex molecules. Its atmosphere is mostly hydrogen laced with exotic vapors. Life as we know it needs calmer conditions. But that doesn't make this world irrelevant to the search for living planets. Hot Jupiters like this one are part of the architecture of planetary systems. They probably formed far from their stars and moved inward. That migration can completely rearrange the inner system where small rocky planets would otherwise live. As a giant moves through, it can shove smaller worlds into new orbits, fling them out of the system, or hurl them into the star. It can destabilize orbits in the habitable zone, or clear the material needed to form Earth-like worlds in the first place. So understanding how hot Jupiters form and how they move does more than explain a curiosity. It helps us sort planetary systems into different categories. Some systems may have violent histories, where giants sweep inward and wreck any potential for stable inner planets. Others may be more gentle, leaving room for small rocky worlds to settle into long, quiet orbits in the habitable zone. This swollen planet, circling so close to its star, is one data point in that larger map. It tells us that in at least one system, a gas giant migrated inward, survived, and now lives in a tight, hot orbit. Add its story to thousands of others, and a pattern begins to emerge. Each world we find, even the ones that could never host life, helps us understand which planetary neighborhoods might be peaceful enough, stable enough, to shelter a world like ours. If you could somehow visit this world, the journey itself would already be beyond anything humans have ever done. At more than 1,000 light-years away, even our fastest spacecraft would take over 11 million years to get there. That's longer than our entire species has been around. So to imagine being there, we have to borrow a trick from science fiction and simply skip the distance. One moment, you're here. The next, you arrive. The first thing that would grab your attention is the star. This sun is hotter and brighter than our own. To your eyes, it would shine an intense white, maybe even with a faint bluish cast. Its light would be harsh, sharp, pouring energy into its surroundings. The whole system would feel overexposed, as though someone turned the dimmer on the universe up too far. As you drift closer to the giant planet, its size would begin to sink in. From 1,000,000 miles away, it would no longer look like a point of light, but a small disk. Keep approaching. At 100,000 miles, that disk would expand until it filled much of your view, a vast curve of cloud and color stretching beyond the edges of your sight. Your sense of scale would start to fail. You'd know in some abstract way that this is just a planet, that it would feel more like a wall of world. The colors would probably not match anything we've seen on Jupiter or Saturn. Jupiter wears bands of browns and creams and reds, formed by familiar chemicals dragged into stripes by its rapid rotation. This planet, with its extreme temperatures and exotic chemistry, might still show banding. Or it might be smoother, or covered in strange patterns we don't really have a template for. It could be dark, almost charcoal, drinking in starlight. Or it might glow with its own subtle light, the way very hot objects do, tinted by the gases that make up its atmosphere. If you tried to go down into that atmosphere, everything would become more and more hostile. Near the top, conditions are already brutal. Temperatures in the thousands of degrees, winds roaring at unimaginable speeds, clouds of metal and rock dust drifting in gas that would destroy any human-made machine in seconds. As you descend, the pressure would climb, the air would thicken, the gas around you would stop feeling like air at all and start behaving more like a hot, crushing fluid. Light from the star would fade, first into a dim, perpetual orange or red glow, then into darkness, lit only by whatever faint infrared glow the planet itself gives off from its heat, trapped below. There is no solid ground waiting at the bottom. No surface to stand on. On a gas giant, the atmosphere just gradually becomes the interior. Go deep enough, and the concepts of gas and liquid start to blur. The material around you would be in a supercritical state. Not really a gas, not really a liquid, but something in between. It would surround you as a dense, hot, continuous medium. Deeper still, if any probe could somehow survive, the pressure and temperature might be high enough to force hydrogen into metallic forms, a layer that could conduct electricity and help generate a magnetic field. Whether this particular planet has that metallic hydrogen layer is not yet clear. Its low density suggests that its core, if it has one, is small or diffuse. We can't peel it open to see. We have only the outside measurements, mass, radius, motion, and from these we build models of the inside. Different models tell slightly different stories. A small compact core, or a fuzzy one, or almost none at all. Some part of the interior may always remain a mystery. And yet, that uncertainty is part of the bigger lesson this world is teaching us. For a long time, our picture of planets came almost entirely from our own solar system. Gas giants, big, cold, far from the star. Rocky planets, small, warm, or temperate, closer in. Ice giants, somewhere in between. It all felt tidy. Then, exoplanets arrived, and the universe politely dropped that tidy picture on the floor. Now we know gas giants can live in deep space, freezing and slow, or cling right next to their stars, blazing hot and heavily irradiated. They can be compact and dense, or puffed up and marshmallow-like. They can travel alone, or share their system with other giants, or be flung away to wander the darkness without a star at all. Rocky planets can be smaller than Earth or several times larger. They might be bone dry or covered entirely in oceans. Their skies could be clear or wrapped in thick blankets of carbon dioxide, nitrogen, or more exotic gases. Some hug their stars so tightly that their rocks melt. Others circle in wide, gentle orbits in the habitable zone, where water could exist as a liquid. Even the ice giant category isn't simple. Some worlds may be deep-water planets with oceans hundreds of kilometers thick. Others might be rich in carbon, with interiors where extreme pressure could turn vast regions into diamond. The label planet turns out to contain more variety than our entire early imagination allowed. Every new instrument we build reveals something we didn't expect, a different kind of orbit, a strange kind of atmosphere, a planet that breaks a rule we did not realize we were relying on. The universe keeps surprising us, and this particular world, so huge, so light, so close to its star that it is being cooked from the outside in, is one of those surprises. It's not just a record holder for size, it's an example of what happens when you push planetary physics to extremes. Take familiar ingredients, hydrogen, helium, a bit of heavier material, and put them under conditions very unlike anything in our neighborhood. You get something that looks almost impossible by the standards we took for granted. So why spend time talking about it at all? Why devote telescopes, research, energy, and years of human effort to a world we will never visit? There are a few layers to that answer. The first is simple. We are curious. Humans have always wanted to know what's beyond the next hill, beyond the next ocean, beyond the next star. That urge is not practical in the narrow sense. Learning that a planet 1,000 light years away is puffed up and low density will not directly fix your car, cook your dinner, or solve your inbox. But the same instinct that drives us to understand this giant planet is the instinct that gave us every scientific advance we rely on now. We push into the unknown because not knowing bothers us. Knowledge has its own value. When we describe this world, add its properties to our shared understanding, we are making the universe a little less opaque. That matters, even if no gadget ever emerges from this specific discovery. The second layer is about context. Right now, we only have one solar system we can examine up close. If we based all of planetary science on that one example, we'd mistake local quirks for universal rules. Jupiter might seem like the template for all gas giants. Earth might seem like the natural way for a rocky planet to look, but they're just one sample each. Exoplanets give us the rest of the dataset. By studying hundreds of gas giants across many different systems, we can see which features are common and which are rare. Is a dense, compact Jupiter-like giant the norm, or a puffy, inflated giants like this one more common than our own system suggests? How often do they stay put, finding behaviors we don't see at home, like extreme inflation, forces us to refine our theories? We're no longer just explaining Jupiter. We're explaining Jupiter, and this giant, and WASP 79b, and KELT 9b, and all the others at once. That makes our understanding stronger and more general. Third, the tools we create to do this kind of delicate astronomy often turn out to be useful elsewhere. The ability to measure tiny changes in light very precisely does not only help us find planets, it filters into medical imaging, industrial inspection, communication technologies, and more. Basic research has a long history of paying unexpected dividends. And then there's the deepest reason. We want to understand our place in the universe. Are we alone? Is Earth a rare exception, or just one of many worlds where chemistry has had enough time to wake up? These questions are not new. People have been asking them in one form or another for thousands of years. What is new is that, For the first time, we have tools that can actually start to answer them. This particular giant is not a home for life. It is far too hot. It has no solid surface. Its atmosphere is made mostly of hydrogen and exotic high-temperature vapors. But that doesn't make it irrelevant to the life question. Giant planets shape the architecture of their solar systems. If they migrate inward, they can scatter or destroy small rocky planets in the habitable zone. If they stay in the outer regions, they may help shepherd debris, deliver water, and stabilize orbits. Understanding how giants behave when they move, how fast helps us understand which kinds of systems are more likely to host Earth-like planets in calm, stable orbits. In that way, this bloated world is one tile in a very large mosaic. On its own, it doesn't tell us whether life is common. Combined with thousands of other tiles, it slowly reveals which patterns in a planetary system make life more or less likely. There's one more layer too, and it's a human one. Children growing up now will never remember a time before exoplanets. To them, the idea that stars have planets is just normal. They will learn that we have catalogued thousands of worlds, that we can study their atmospheres, that finding Earth-like planets is an active project, not a fantasy. Some of those children will become the scientists who point the next generation of telescopes at the sky and make discoveries we can't even predict. Others will never work in science at all, but knowing that the universe is full of real planets, not just stars, will quietly shape how they think about existence. Telling the story of worlds like this, one is part of inspiring that next wave of curiosity. Hearing that there is a planet bigger than Jupiter that would float in water doesn't just give you a fact, it stretches your sense of what is possible. It makes the universe feel more alive, more intricate, less like an empty backdrop. And underneath all of that is an even deeper connection. Every atom in your body has had a long life before becoming part of you. The carbon in your cells, the oxygen in your lungs, the iron in your blood. Those elements were forged in stars. Some were made quietly in stellar cores, and then released when stars shed their outer layers. Others were created in violent explosions when massive stars died. In either case, those atoms were flung into space, mixed with gas and dust, and slowly recycled into new generations of stars and planets. Eventually, some of that material ended up here, in our solar system. It became Earth. It became you. This giant planet is made of the same stuff. Hydrogen atoms on that world are identical to the hydrogen atoms in the water you drink. Helium atoms in its atmosphere are the same helium we put in balloons. At the most basic level, there is no alien matter and human matter. There is just matter, shaped by physics into stars, planets, cells, and consciousness. We are connected to this world not just by light and mathematics, but by our shared origin in ancient stars. When we study it, we are studying what the universe does with its building blocks under different conditions. In a very indirect way, we are also studying the backdrop that allowed us to exist. Modern astronomy keeps returning to this theme. We are not outside the universe, looking in. We are part of it. The same laws of physics that govern the crushing interior of this hot giant govern the chemical reactions in your brain as you listen to this. The same gravity that holds this planet in its tight orbit holds you to the ground. The universe is not a distant, separate thing. It is the context that made you possible. Seeing that clearly can shift how you move through your everyday life. It doesn't change your to-do list, but it changes the frame. Your problems are still real, so is your joy. But they play out against a backdrop of stars and planets, of galaxies and cosmic history. Somewhere more than 1,000 light-years away, a vast underweight planet is circling its star, indifferent to us. It was orbiting before humans existed. It will likely still be there, in some form long after we are gone. And yet, we know about it. We have drawn its orbit. We have measured its size. We have estimated its temperature. We have speculated about its winds and clouds. and rain made of metal. That act of knowing, of caring enough to find out, lets us reach a little beyond our small corner. For a moment, our minds stretch to match a universe that is much bigger than we are. We happen to be living at a special time. For almost all of human history, we did not know whether other worlds existed around other stars. Now we know they do. We are the first generation to move from maybe to definitely, from myth to measurement. We are the first to study in detail the atmospheres of planets we will never visit. We are the first to be able to say, with data behind us, that the night sky is full of suns with their own families of worlds. That knowledge changes how the stars look. They are no longer just points of light. They are addresses. As you go back to your life, you don't have to hold all of this in your mind all the time, but it's there when you want it. You can look up at the night sky and remember that among those many stars, there is one with a planet more than twice the size of Jupiter, inflated and glowing in fierce heat. You can let that thought sit beside the ordinary details of your day and see if the contrast changes anything for you. The universe is vast. We are small. Both of those statements are true, but being small does not make us irrelevant. We are the way the universe has found to look back at itself and asked what else is out there, and as long as we keep asking, keep measuring, keep wondering, worlds like this, one will continue to step out of the darkness and into our understanding. If you zoom out from this one strange planet and look at the story of how we even learned to find worlds like it, things get even more interesting. For a long time, astronomers tried to find planets around other stars and failed, not because they were careless, but because the problem is hard in a way that is almost cruel. The signals are tiny, the noise is huge. For decades, people invented clever methods, collected mountains of data, and still came up empty. In the 1940s and 50s, there was a moment when it looked like the hunt was over. A few astronomers thought they had finally done it using a method called astrometry. That just means watching how a star moves across the sky, very, very precisely. If a star has planets, it doesn't travel in a perfectly straight line. It wobbles a little as the planets tug on it. Measure that wobble, and you might infer the invisible worlds. One of the most famous claims involved Barnard's star, one of our closest stellar neighbors. A Dutch astronomer named Peter van der Kamp spent decades tracking its position from a single observatory in Pennsylvania. After years of careful measurements, he announced that Barnard's star had not one, but two Jupiter-sized planets orbiting it. The idea was thrilling. If one of the nearest stars had big planets, then planets must be everywhere. The newspapers loved it. Other astronomers were excited too. It felt like the universe had widened overnight. But science doesn't stop at excitement. Other teams turned their own telescopes on Barnard's star, repeated the measurements, and tried to see the same wobbles. They couldn't. The pattern just wasn't there in their data. Slowly, people realized what had gone wrong. Every time Van der Kamp's telescope was repaired or adjusted, those changes introduced tiny shifts into the data. The telescope was moving, not the star. Those little jumps in the instrument mimicked the signal of orbiting planets. Van der Kamp himself never accepted that conclusion. He defended his planets until he died in 1995. Ironically, that was the same year the first confirmed planet around a sun-like star was announced. He was right that planets exist around other stars. He was just wrong about that particular star. That story hung over the field like a warning sign. It taught astronomers how easy it is to fool yourself when the signals are tiny and the desire to find something is huge. So the community got stricter. Claims of new planets had to survive much tougher tests. Independent teams had to confirm the result with different instruments, or even different methods, entirely. Every possible source of error had to be checked and rechecked. The standard became, if there is any other explanation that fits the data, it's not a planet yet. That is why the discovery of 51 Pegasi b in 1995 was handled so carefully. Michel Mayor and Didier Queloz had found that Jupiter-mass planet hugging its star with the radial velocity method watching the star's light shift back and forth as it wobbled. But they knew that stars are not perfectly quiet. They can pulsate, they can have spots, they can have unseen stellar companions. Any of those could mimic a planet's pull, so they kept collecting data. They watched the star over and over. They looked for links between the signal and the star's own activity. They double-checked their uncertainties. Only when they were satisfied that the wobble really was the pull of an orbiting world did they publish. Even then, others were skeptical. A Jupiter-mass planet on a 4-day orbit sounded impossible. But when another team, led by Jeff Marcy and Paul Butler, turned their own instruments on 51 Pegasi, they saw the same pattern in the star's motion. The planet was real. That cautious culture is still in place today. It's the reason we can trust the discovery of the giant we've been talking about. When the Hathi 8 network first saw the star in Hercules dimming periodically, the astronomers did not rush out to declare they'd found the largest planet ever. They took a breath. Then they gathered more data. They used bigger telescopes to check the star's radial velocity. They checked for signs that the signal might be caused by a pair of stars eclipsing each other, or some other trick. Only when independent lines of evidence all pointed to the same conclusion did they call it a planet. That is why we can say with confidence that this world exists. It's not just one method. It's multiple, all converging on the same answer, after years of scrutiny. Now, this planet is one record holder, but it is not alone at the edges. Take KELT, DEEK, ELT 9b, for example. It's one of the hottest exoplanets we know. Its dayside temperature is over 4,300 Kelvin, around 7,600 degrees Fahrenheit. That's hotter than the surfaces of some stars. At those temperatures, molecules can't really stay together. The atmosphere is full of single atoms, hydrogen, helium, iron, magnesium, drifting as a kind of atomic fog. The planet is so intensely heated that its atmosphere is slowly being stripped away into space. On the other end of the scale, there are worlds like OGL, EAEKA 2005, BLG, BLG 390L. It was discovered in 2005 using gravitational microlensing, a technique that depends on one star passing in front of another and magnifying its light. This planet is estimated to have a surface temperature around 50 Kelvin, about 364 degrees Fahrenheit, colder than Pluto. It orbits far from a small, faint star, receiving barely any warmth. Almost certainly frozen, dark, and lifeless. There are extremes in density too. Some planets are so dense that they challenge our imagination. Candidates like Kepler 131c may have densities more than 30 times that of water. For comparison, iron is about 7.9 times denser than water. Lead is about 11.3. A planet with density above 30 would have to be made mostly of very heavy elements, crushed under enormous pressure. We don't fully understand how such worlds form. On the other side, we have the least dense giants. Aside from the world we've been focusing on, another similar case is WASP 193b, which has a density of about 0.059 grams per cubic centimeter. That's slightly less than this planet's. Both are incredibly puffy, almost cotton candy worlds. Understanding why these few hot Jupiters bloat so much, while others with similar temperatures and masses stay more compact, is an active puzzle. Orbits stretch to extremes as well. Some planets, like K2 137b, race around their stars in just over 4 hours. They complete more than 5 full orbits in a single Earth day. At such close distances, they are locked with one side permanently facing the star, one side permanently facing away, and their surfaces are baked by constant radiation. At the opposite end, some directly imaged planets sit hundreds or even thousands of times farther from their stars. than Earth's, their orbits may take thousands of years to complete. They probably formed in different ways, more like small stars collapsing from gas than like planets calmly accreting from a disk. Each of these record holders, the hottest, the coldest, the densest, the puffiest, the fastest, the slowest, traces out the edges of what planets can be. They define the boundaries of the possible. Any theory of how planets form and evolve has to match not just the average worlds, but also these weird outliers. Our huge, low-density giant in Hercules is one of those boundary markers. It pushes on our models of how gas giants respond to heat. If our theories continue to reproduce a planet this inflated, they're missing something important. The star it orbits matters too. This is an F-type star. That's just a way of saying it's hotter and more massive than our Sun, but not so extreme as the very hottest stars. Its surface temperature is somewhere between about 6,000 and 7,500 Kelvin, compared to the Sun's roughly 5,800 Kelvin. It shines brighter and puts out more energy, but it will burn through its nuclear fuel faster and live a shorter life. Our Sun is expected to spend about 10 billion years in its stable, hydrogen-burning phase. An F-type star like this, one might only get 5 to 7 billion years before it starts to change, swell, and eventually become a red giant. These stars are attractive targets for exoplanet searches. They're bright enough that we can study them easily, but not so hot that their ultraviolet radiation completely overwhelms the signals we're trying to see from their planets. They also aren't rare. Maybe a few percent of the stars in our galaxy are F-type. A few percent of hundreds of billions is still billions of stars. This particular star rotates relatively slowly, which is important. Fast-rotating stars smear out their spectral lines, making it hard to measure tiny Doppler shifts. A slow spin keeps those lines narrow and sharp, making the radial velocity technique more precise. Its chemical makeup plays a role as well. Astronomers talk about a star's metallicity to describe how much of its material is made up of elements heavier than helium. Stars with higher metallicity tend to have more giant planets, probably because there was more solid material in the original disk to build planetary cores. This star has a composition similar to our Sun's, which is a good environment for forming at least one large planet. So the star's mass, temperature, age, rotation, and composition all feed into the story. They shape how much energy the planet receives, how long the system has had to evolve, and how easy it is for us to detect and study the planet. You can't really talk about one without keeping the other in mind. Stars and planets are a package deal. The puzzle of why some hot Jupiters are so inflated has driven a lot of theoretical work in the last decade. Basic models of gas giants say that for a given mass, a planet should settle into a certain size as it cools and contracts over time. Jupiter fits those expectations pretty well. But then the first hot Jupiters showed up, and many of them were larger than those models allowed, especially after you account for their ages. Intense heating from the nearby star was the obvious suspect. These planets receive hundreds or thousands of times more energy from their stars than Jupiter does. That radiation puffs up their outer layers. When scientists built detailed models that included this heating, they could explain some of the extra size, but not all. For the most extreme cases, including this planet, just shining a lot of light on the outside isn't enough. The models still predict smaller radii than we actually see. That means extra heat must be getting into the deeper interior and staying there. One leading idea involves energy being carried downwards from the hot upper atmosphere into the planet's interior. In many models, the energy deposited high up just gets radiated back out into space. It doesn't penetrate very deep. But if some mechanism can grab part of that energy and drive it inward, it can warm the inside and inflate the planet from within. One such mechanism is called ohmic dissipation. The intense radiation from the star can strip electrons from atoms in the upper atmosphere, making the gas partially conductive, like a weak metal. As winds blow this conducting gas through the planet's magnetic field, they induce electrical currents. Those currents run through the interior and lose energy as heat. It's like wiring the planet up as a giant, leaky electrical circuit that turns stellar energy into internal warmth. Another idea looks at the way the atmosphere and interior might be coupled. The huge temperature difference between the day side and night side drives strong winds and circulation patterns. Those flows could interact with deeper layers, stirring them and transporting energy downward in complex ways that keep the planet hot and bloated for far longer than simple cooling models would suggest. A third possibility is that the details of the atmospheric composition matter more than we expected. Certain molecules, at certain altitudes, might act like very effective insulators. They could absorb and re-emit radiation in ways that trap heat, slowing down the rate at which the planet cools and contracts. In that case, two hot Jupiters with similar masses and orbits, but slightly different atmospheric chemistry could end up with very different sizes. Most likely, the real answer isn't just one mechanism, it's a mix. Different processes might dominate in different planets, depending on their specific conditions. The field is still working toward a unified picture that can explain both typical hot Jupiters and outliers like this one. To make progress, scientists rely heavily on computer simulations. They build three-dimensional models of planets, layer by layer, following how energy moves, how winds blow, how chemistry changes with time. They run these models under different assumptions and then compare the results to observations. If a model can reproduce the sizes, temperatures, and spectra we actually see, it gains credibility. If it fails, it points to missing physics. Our record-breaking planet is an important test. Any theory that claims to explain hot Jupiter inflation can't just match the middle of the population. It has to match the extremes. If your model can't inflate this world to the size we observe, you're not done yet. And all of this connects back, indirectly, to the question of life. On the face of it, this giant planet has nothing to do with habitability. It is far too hot. Its atmosphere is wrong for life as we know it, but that's not the point. The point is that giant planets are the architects of their systems. If a gas giant forms far out and then migrates inward, it doesn't slip through quietly. Its gravity can fling smaller planets into new orbits, or out of the system entirely. It can throw rocks and ice inward, or outward. It can plow through the region where Earth-like planets might otherwise grow, scattering the building blocks before they have a chance to assemble. A system that goes through a violent migration phase may end up with a hot Jupiter close in and very little left in the habitable zone. Our solar system does not have a hot Jupiter. Jupiter and Saturn stayed relatively far out. That stability may have been crucial. It gave the inner planets time and space to form and settle into stable orbits. If Jupiter had fallen inward early on, sweeping through the region where Earth was forming, our world might never have existed. So when we study hot Jupiters like this one, we are also studying the dark side of planet formation, the ways in which giant planets can sterilize or reshape their systems. Knowing how often that happens, and around what kinds of stars, helps us figure out where to look for calmer systems where rocky planets in the habitable zone had a better chance. There is a broader shift hidden in all of this. For a long time, we quietly assumed that other planetary systems would look like ours. Small rocky planets in close, gas giants, farther out. Maybe a belt of icy leftovers at the edge. Hot Jupiters shattered that picture. They showed us that planets can end up in orbits we never considered, in configurations we never predicted. That realization forces us to loosen our imagination. Maybe habitable planets exist in places we once would have ruled out. Maybe life can adapt to environments we don't yet think of as friendly. Maybe our picture of a normal system is just one example in a huge gallery of possible arrangements. The more we learn about extremes like this distant giant, the more we understand the full range of what planetary systems can be. That understanding, even when it centers on worlds where life probably cannot exist, helps us think more clearly and more creatively about where life might exist. It teaches us that the universe is not obliged to match our expectations, and that, in science is often where the most important discoveries begin. Since this planet was first announced in 2017, it hasn't been left alone for a single moment, scientifically speaking. One after another, different telescopes have taken their turn, staring at this star in Hercules, each adding a little more detail to the picture. Ground-based observatories have watched transit after transit, measuring exactly how deep the dip in starlight is and exactly when it happens. That might sound repetitive, but it's how you go from "we think there's a planet here" to "we know its size and orbit with real precision." Above Earth's atmosphere, space telescopes have joined in. Some have looked for tiny irregularities in the transits that could hint at an extra planet, or even a moon tugging on the giant's orbit. Others have focused on the spectrum of the light itself, searching for the chemical fingerprints of gases high in the planet's atmosphere. The Hubble Space Telescope, famous for its beautiful images of galaxies and nebulae, has quietly been doing this kind of delicate exoplanet work as well. When this planet passes in front of its star, Hubble watches for specific colors of light that are slightly dimmed. That's how it looks for water vapor and other molecules in the upper atmosphere. The signal is tiny, barely there, but Hubble's stability and sensitivity make it a good tool for this kind of balancing act. The Spitzer Space Telescope, before it was retired in 2020, studied the planet in infrared light. That wavelength range is especially useful for hot Jupiters because it lets us probe different layers of the atmosphere than visible light does. By watching how the planet's infrared brightness changed as it moved around its star, Spitzer helped pin down how heat is shared between the scorching day side and the cooler night side, and what the temperature structure looks like at different depths. Now James Webb has entered the scene, and it changes the game again. Webb has already shown that it can pick out very specific molecules in exoplanet atmospheres with a clarity we've never had before. When it turns its attention fully to this giant, the spectra it collects will let us refine the list of atmospheric ingredients, map how temperature changes with altitude, and maybe even catch hints of weather patterns, hotspots, cooler regions, or unexpected structures in the gas. Meanwhile, the big ground-based telescopes are still far from obsolete. With high-resolution spectrographs, they can see individual spectral lines from molecules in the atmosphere and measure how those lines shift as the planet moves. From those shifts, astronomers can tell not just what is present, but how it is moving. Winds blowing toward us or away from us leave subtle fingerprints. Over many orbits, we can begin to map the flow of gas from day to night and from equator toward the poles. Continuous monitoring from the ground also keeps an eye on the timing and shape of the transits. A hidden planet in the system could tug on the giant, making its transits arrive slightly early or late. A large moon could add its own tiny dips or distortions. So far, there's no clear sign of extra bodies here, but the system hasn't been dismissed. The search is very much alive. All of these observations together have sharpened our view of this world. Early on, its mass was estimated at roughly 1/3 that of Jupiter. As more radial velocity data came in, that estimate shifted upward to about 0.45 Jupiter masses, and the error bars shrank. The radius measurement has likewise become more precise as more transits have been recorded. The orbit is now characterized with much tighter confidence. Its period, its inclination, its shape. This is what scientific progress often looks like from the inside. Not a single eureka moment, but lots of small corrections. Each new observation nudges the numbers a little. Each new instrument trims back the uncertainty. What begins as a faint, fuzzy data point gradually becomes a well-described planet with known mass, known radius, known orbit, and a growing dossier on its atmosphere. And this won't stop. Future telescopes will revisit this star with even better sensitivity. New analysis techniques will squeeze more information from data we already have. The planet that started as a transit signal in a modest survey will eventually become one of the best understood inflated giants we know. The tricks we learn studying it will then be turned on more subtle worlds, smaller, cooler planets, including those in habitable zones where conditions might resemble home a little more closely. That's the pattern. Each discovery is not a finished chapter. It's a starting point. The same is true for the transit method itself. At first glance, a transit just looks like a dip in brightness. Star, planet moves in front. Star dims, planet moves away. Star brightens. But buried in that simple pattern is a surprising amount of information. How deep the dip is tells you how large the planet's disk is compared to the star's disk. A bigger planet blocks more light. Measure that depth carefully, and you get the planet's radius relative to the star. Combine that with a good estimate of the star's size, and you have the planet's actual radius. How long the transit lasts tells you about the path the planet takes across the star. Passing straight across the middle takes longer than skimming across near the edge. Comparing the transit duration with the orbital period lets you figure out the inclination of the orbit, how tilted it is relative to our line of sight, and how close to the star's center the planet's path runs. Even the shape of the transit curve, the way the light dims and brightens as the planet enters and exits, holds clues. Stars are not evenly bright from center to edge. They are brighter in the middle and dimmer near the rim, an effect called limb darkening. As the planet moves across different parts of the stellar disk, the rate of change in brightness shifts. Modeling that carefully tells us both about the star's surface brightness profile and about the planet's exact path. Then you can start adding color. If you observe the transit at many different wavelengths, you can see how the depth of the dip changes with color. An atmosphere that contains molecules that absorb specific wavelengths makes the planet look slightly larger at those wavelengths, because those layers are effectively opaque. That's transmission spectroscopy, and it turns a simple dip in brightness into a way to read the planet's atmospheric composition. Eclipses add another layer. When the planet slips behind the star, its own light is briefly blocked. If you compare the system's brightness just before and during the eclipse, you can isolate and subtract the planet's contribution. That gives you a direct measurement of how much light the planet emits or reflects, especially in infrared. From that, you can estimate the temperature of its day side and learn which molecules are glowing or reflecting there. Phase curves extend this idea throughout the orbit. As the planet moves around the star, the fraction of its day side that faces us changes. At some points we see mostly night side, at others we see mostly day side. By tracking the system's brightness over a full orbit, astronomers can build a map of how hot different longitudes are and how efficiently heat is moved from the day side to the night side. You can even infer where the hottest spot is. It's often shifted away from the point directly under the star because of winds. All of these techniques have already been used on hot Jupiters like this one. Together, they take us from "there is a planet" to "we have a rough weather map" of a world we will never visit. The future will push this even further. New missions are planned specifically to find and study planets in regimes we haven't explored as deeply yet. The Plato mission, set to launch in the coming years, will look for Earth-sized planets around Sun-like stars, especially in their habitable zones. It will find worlds with orbits measured in months or years, rather than days. Planets where liquid water might exist on the surface. Another mission, Ariel, is designed to focus on atmospheres. It will study the skies of around 1,000 exoplanets across a wide range of types, hot Jupiters, warm Neptunes, super-Earths, and build a statistical picture of how atmospheric composition and structure depend on things like planet mass, temperature, and distance from the star. Our record-breaking giant will be one point in that larger cloud of data. On the ground, a new generation of extremely large telescopes will soon start work. Their enormous mirrors will collect far more light than anything we've built before, making it possible to directly image some planets around nearby stars and disperse their light into spectra. For some systems, we may actually see Earth-sized planets as tiny points next to their stars and analyze their atmospheres for signs of water, oxygen, or other gases that might hint at biological activity. All of these advances rest on what we have already learned. The methods we're perfecting now on big, bright targets like hot Jupiters will be absolutely essential when we turn our attention to smaller, dimmer, more Earth-like worlds. It's much easier to refine a technique on a large, dramatic signal and then apply it to a subtle one than to start with the hardest case first. So this enormous, underweight, overheated planet is more than just an oddity. It's a training ground. A step on the road toward understanding planetary systems in all their variety, and toward one of the biggest goals in science, recognizing, in the faint light of a distant star, the signs that a small, rocky world might be alive. Someday, the same tools that are now teasing out the secrets of this giant atmosphere may be used to study a pale, distant planet with a sky and temperature not so different from our own. If we ever do find a planet that truly whispers life in its atmosphere, it won't come out of nowhere. It will rest on the shoulders of worlds like this one. Hot Jupiters, super Earths, mini Neptunes, puffy giants that could float in water. Every strange, unfriendly planet we study is quietly building the toolbox we will one day use on a small, temperate world with an odd mix of gases we can't explain. Away with rocks and volcanoes, that first unmistakable sign of biology, if it ever comes, will be written in a language we learned by practicing on hostile worlds. You never really know which discovery will matter most, or which technique will end up being repurposed for something no one had in mind at the start. You follow curiosity because understanding is valuable even before it's useful. This giant planet is exactly that. A curiosity that slots into a much larger project. One speck in a growing catalogue of thousands already found, and millions more still unseen. It happens to hold the record for size right now. One day, another planet may take that title. This one might become just a footnote, or it might remain a stubborn puzzle we never fully solve. Either way, the important thing is that we looked, we noticed, we measured, we tried to understand. In a universe that is mostly unknown, every scrap of knowledge we manage to pull out of the dark is a kind of quiet victory. If you step back for a moment from the physics and think about where exactly this world resides, there's another layer of charm. Its star sits in the constellation Hercules. People have been tracing shapes in those stars since long before anyone knew what a star actually is. The ancient Greeks looked up, saw this pattern in the sky, and imagined a hero, the strong man who completed 12 impossible labors. To them, the stars were light set into a turning sphere. The idea that each might be a distant sun, with its own retinue of planets, would have been more fantastical than any myth. Hidden among those points of light is this star in Hercules with a swollen planet, hugging it in a furnace-hot orbit. The Greeks knew the shape, but not the story. The universe hadn't yet given them the tools to read what those stars really were. It took a long chain of ideas to get from lights on a dome to a puffy planet that could float in water. Copernicus shifted Earth from the center of the universe. Galileo pointed a small telescope at the sky and saw moons circling Jupiter, proving that not everything turns around us. Newton described gravity with equations, letting us calculate orbits before a planet ever gets there. Spectroscopy showed that stars are made of the same elements we find on Earth. Relativity refined our ideas of space and time, and then, in the 1990s, instruments finally became precise enough to detect the tiny tugs and faint dips that betray planets around other stars. Each step depended on the ones before. Each generation inherited tools and knowledge, nudged the boundaries a little farther, and left something for the next. When we celebrate the discovery of this giant, we're really celebrating that whole edifice. Centuries of people willing to ask hard questions about the sky. This connects directly to another idea that sounds simple, but ends up being subtle: the habitable zone. Around every star, there's a region where, in principle, a planet on the right kind of orbit could have liquid water on its surface. Too close in, and any water would boil away into steam. Too far out, and it would freeze solid. In between is the Goldilocks band where water can stay liquid, and liquid water is the one ingredient every known form of life depends on. Exactly where that zone lies depends mostly on the star's brightness. Hotter More luminous stars have habitable zones that are farther out and wider. Cooler stars have tighter, closer, inhabitable zones. But the picture isn't just about distance. A planet's atmosphere matters too. A thick blanket of greenhouse gases can keep a world warm, even if it doesn't get much starlight. A thin, clear atmosphere might let a planet freeze even inside the right region. Hot Jupiters like our record holder live far inside this habitable zone. They are much too close, far too hot for liquid water. But they still teach us something important about habitability, just not in the way you might expect. These giants didn't form where we see them now. They almost certainly started life farther out, where ices could condense and material could pile up into a massive core. At some point they moved inward, spiraling toward their stars. As they did, they would have passed through the habitable zone, plowing gravitational chaos in front of them. Any small rocky planets that happened to be there would likely have been scattered into eccentric orbits, thrown into the star, or flung entirely out of the system. So if we see a hot Jupiter sitting close to its star, that system probably isn't a good place to hunt for an Earth-like world quietly orbiting in the habitable zone. The odds are that region was disrupted. On the other hand, when we see a system where any giant planets stayed out at Jupiter-like distances, that's more promising. The inner regions might have had the peace and quiet needed to form and keep a habitable planet. In this way, the giant we've been talking about becomes part of the triage process. With thousands of systems known but limited telescope time, astronomers need to choose their targets. Understanding how hot Jupiters migrate and how they reshape their systems helps point the most powerful instruments at the stars most likely to harbor Earth-like worlds that survived. And it's not just big observatories that help with this work. Amateur astronomers, people with backyard telescopes, modest cameras, and a lot of patience play a real role in exoplanet science. Most discoveries are made with professional instruments, but once a transiting planet is known, its transits are there for anyone on Earth's surface who can see the star and measure brightness carefully. Small telescopes can do this. With the right setup, an amateur can record the dip in light as a planet passes in front of its star. They can help refine the timing of transits, check whether the signal is stable over years, and search for small deviations that might hint at other bodies. Because amateurs are spread all over the world, they can often catch events that professional observatories miss due to weather or scheduling. For a planet that causes a relatively deep dip, around 2.5%, like this one, the signal is actually within reach of dedicated amateurs under good conditions. Some have already contributed data, helping to pin down this giant's orbit more precisely. There's something quietly beautiful about that. The universe doesn't belong to institutions. It belongs to everyone with eyes, curiosity, and the willingness to watch carefully. The line between professional and amateur in astronomy is thinner than it looks. On both sides of it are people staring at the same star, trying to read the same tiny changes in light. Even with all this attention, real mysteries remain. We still do not fully understand why some hot Jupiters puff up so dramatically, while others with very similar masses and temperatures stay more compact. The data show a lot of scatter. Two planets can sit under nearly identical stellar conditions, but one inflates to cartoonish size while the other behaves more like Jupiter. Our current models can explain some of this, but not all. Something, maybe several somethings, is missing. The history of each planet may matter. A giant that migrated inward very early, when its star was young and energetic, might have been heated differently from one that arrived later. The path it took inward could have changed how much tidal heating it experienced. The size and composition of any core could affect how the interior responds to heating from above. But even when we include these possibilities, the range of radii we see in real planets is wider than our equations, like. The atmospheres add another layer of puzzle. Observations have revealed that hot Jupiter atmospheres are not all alike. Some are hazy or cloudy, with muted spectral features because tiny particles scatter and blur the light passing through. Others are clear, letting us see deep, strong molecular signatures. You might think hotter planets would always be clearer, or that certain temperatures would always produce specific clouds. But reality is more complicated. Cloud formation depends on temperature, pressure, how vigorously the atmosphere is stirred, and what elements are available to condense. Hazes can form from chemical reactions high in the atmosphere, turning simple molecules into complex particles that hang in the air. Magnetic fields might steer winds and affect where clouds form and how thick they are. Put all of this together, and you get a rich variety of skies that we're only beginning to classify. Our inflated record holder, sitting at an extreme end of the size scale, is a key test case. Whatever processes drive this kind of inflation must be turned up to maximum here. By studying it in detail, measuring its spectrum across many wavelengths, tracking its temperature pattern, watching it over time, we may be able to tease out which mechanisms dominate. These oddly swollen planets lead naturally into a more philosophical shift. For most of human history, questions about other worlds lived in the realm of imagination. Philosophers debated whether worlds existed beyond Earth. Poets wrote about crystal spheres and endless heavens. But there was no data. The universe was an ocean of guesses. Now, in just a few decades, we've gone from speculation to measurement. We know that exoplanets exist. We know their sizes, their masses, their orbits. We can infer their temperatures. In some cases, we can detect what their skies are made of. And what we found would have sounded like science fiction even to scientists from a few generations ago. Gas giants in orbits so tight they complete a year in a few days. Planets that are so light and puffy they would float. Scorching worlds where iron might literally rain out of the sky. The universe, it turns out, is not just a bigger version of our backyard. It is constantly inventing ways for matter to arrange itself that we never thought of. That realization carries a quiet warning. If the cosmos can surprise us this much with planets, it might surprise us just as much with whatever else is out there. Life, intelligence, phenomena we haven't named. We shouldn't assume that anything beyond Earth will look like a simple copy of what we already know. Being open to surprise is not just a nice attitude, it's almost a requirement for good science. Many of the most important advances have come from anomalies, results that didn't fit the prevailing theory and refused to go away. Hot Jupiters were one of those anomalies. The old models said gas giants should form far out and stay there. Then these blazing close-in giants showed up and forced a rewrite. The universe tapped us on the shoulder and said, "You forgot a few steps. We don't know what the next big surprise will be." That's part of what makes this field exciting. The future is genuinely unknown. Somewhere in the data already collected, or in the light yet to be captured by a future telescope, there are patterns we don't yet know how to see. Looking at the timeline of exoplanet science gives you a sense of how fast things can shift. The first planet around a sun-like star was confirmed in 1995. 30 years later, we know of more than 5,700 exoplanets. Early on, we added them one by one, a slow trickle. Then came missions like Kepler and TESS, and the trickle became a flood. If that pace continues, by the middle of this century we may have tens of thousands of confirmed planets. But even more important than the raw number will be the depth of our knowledge. Right now, detailed atmospheric studies are reserved for a small fraction of these worlds. In a few decades, that kind of characterization may be routine for many planets, including some Earth-sized ones. By then, it's entirely possible that we will have seen a spectrum from a distant world that cannot easily be explained without invoking life, some persistent, planet-wide chemical imbalance that geology alone struggles to produce. Or it may be that we've searched many likely worlds and found nothing, at least nearby, hinting that life is rare. Either outcome would profoundly change how we think about ourselves. When future astronomers look back, this bloated planet in Hercules will probably seem like an early stepping stone, a representative of the time when we were still mapping out the extremes and learning how to read the faint signatures in exoplanet-like curves and spectra. They will have tools we can't picture the way we have tools Newton could not have imagined. Each generation inherits a sky full of questions, answers a few, and adds better questions for the next. That continuing growth of understanding is one of the most hopeful things we have, especially in a world where so much feels uncertain. It helps sometimes to bring all of this down to a very personal scale. You are a conscious being living on a small, rocky planet orbiting an ordinary star in a galaxy of hundreds of billions of stars. That galaxy is just one of trillions. The universe is almost 14 billion years old. It will keep going for trillions more. On those timescales and distances, a human life is the briefest flicker. The giant planet we've been talking about could swallow 12,000 Earths by volume. The light from it takes 1,000 years to get here. It is vast and remote in a way that is hard to truly feel, and yet, you exist. A temporary arrangement of atoms, shaped by the same physics that shapes that huge planet and its star, has somehow become aware enough to look up and wonder about distant worlds. That's odd. That's fragile. That's remarkable. When you look at the night sky, you're not just seeing points of light, you're participating in a chain of curiosity that stretches back to the first humans who stared up and asked what those lights were. You are linked to the thinkers who guessed at other worlds, to the observers who built telescopes, to the scientists who turned faint wobbles and tiny dips into planetary catalogues. You are also linked across space. The hydrogen in your water is the same kind of hydrogen that fills this giant planet. The iron in your blood was forged in supernovae, like the ones that seeded the cloud from which its star formed. Your atoms have traveled a long, long way to become you. The planet doesn't know you exist. It will keep circling its star, whether or not anyone pays attention, but you know it exists now. You've added it, in some small way, to your mental map of reality. That connection matters, even if just to you. It is one of the ways science stretches your world, not by changing your physical surroundings, but by enlarging the space inside your mind. Stories like this remind you that your daily worries and joys play out within a universe that is much larger and stranger than anything on your calendar. That doesn't make those worries vanish, but it can put them in a different frame. It gives you something to return to in quiet moments. The knowledge that reality includes gas giants that float and rain iron, stars that die and recycle, planets that exist only as tiny dips of light in a detector. Gas giants themselves are an invitation to think differently about worlds. On Earth, we have a crisp idea of a planet's surface. There is ground. Above that, there is air. You can stand, look up, and draw a line where the atmosphere ends and space begins. The atmosphere is a thin shell over a solid ball. On a gas giant, that neat division breaks down. There is no literal surface you can point to. As you descend, the pressure gradually increases, the gas thickens. At some depth, it behaves more like a fluid than what we'd call air. Deeper still, it becomes a supercritical medium, something not quite gas and not quite liquid. There's no sharp boundary, no floor to stand on and say, here the planet begins. Even the radius we assign these planets is a convention. For Jupiter and Saturn, astronomers typically define the radius at the level where the atmospheric pressure equals 1 bar, roughly Earth's sea level pressure. That's a useful standard, but it's not a physical wall. For hot Jupiters with hugely expanded atmospheres, the problem is even fuzzier. Their outer layers blend gradually into space in an extended envelope. This doesn't break the science. We're careful to define what we mean and use the same definitions when comparing worlds. The transit depth and radial velocity signals themselves are crisp. The uncertainty is not in the data, but in the way we choose to draw lines around things that are inherently continuous. It does, however, highlight something important. Gas giants are not just big Earths with thick skies. They're fundamentally different types of objects. Extended, layered, with insides that have more in common with stars and high-pressure physics than with continents and oceans. For Jupiter, we've been able to probe that interior in unusual detail thanks to the Juno spacecraft, which has been orbiting and mapping its gravitational field. The variations in gravity tell us how the mass is distributed inside. The results show that Jupiter's core is not a simple, dense ball sitting under a neat envelope. It seems to have a dilute core, with heavy elements mixed throughout a large region. The transition from core to envelope is fuzzy, not sharp. For exoplanets, we don't have spacecraft measuring their gravity up close. All we get are total mass, radius, and whatever we can infer from light. For our record-breaking giant, the extremely low density tells us that it cannot have a huge, compact core. Either any core is small, or it's spread out and mixed with the surrounding hydrogen and helium, or perhaps it never fully formed. Unraveling which of those is true requires models, not direct probing. To tackle questions like that, scientists build computer simulations. These are not simple cartoons, but detailed numerical experiments that track how pressure, temperature, and composition change with depth and time. For atmospheres, they divide the gas into cells and calculate how radiation from the star is absorbed, how it heats different layers, how winds develop and move heat around, how chemicals react to form or destroy molecules and hazes. For interiors, they solve equations that describe how a planet cools and contracts over billions of years, how heat moves by convection or radiation, how materials compress under enormous pressures. Then they try to couple the two, the atmosphere on top, the interior underneath, because the boundary between them is not really a boundary at all. Heat leaking out from below and heat pouring in from above interact. To understand a hot Jupiter properly, you need both parts talking to each other. These simulations run on supercomputers and improve continually. They can now model full three-dimensional flows, track hundreds of chemical species, and generate simulated spectra and light curves that can be compared directly to observations. When we detect a certain molecule or see a particular phase curve pattern, we use those models to interpret what it means about the real planet's structure and behavior. The dance between observation and simulation is where much of the progress happens. New data reveals a pattern. Existing models fail to reproduce it. That failure points to missing physics. The models get updated. They make fresh predictions. Observers test them, round and round, deeper each time. Why put so much effort into stories like this, especially in a world that is already overflowing with information and distraction? Part of the reason is that some topics are worth slowing down for. The fact that other worlds exist, that we can study them, that they are stranger and more diverse than we imagined. That's one of the profound truths of our era. It deserves more than a headline you scroll past. Spending an hour or two really sitting with a single planet is a way to step outside the churn of daily life. It's an exercise in sustained attention on something that has nothing to sell you, nothing to argue with you about, no urgency attached at all. You're letting your mind stretch out over light years and billions of years, over physics and history and philosophy, in one continuous thread. In practical terms, knowing about this particular planet won't fix anything in your day. But humans don't live on practicality alone. We need beauty, meaning a sense that we are connected to something larger than our immediate concerns. The story of a planet twice the size of Jupiter, light enough to bob on water, roasting in orbit around a distant star, is one of those threads that tie us to a larger tapestry. Carrying that awareness changes how the ordinary world feels, even if just a little. It can shrink your problems when they loom too large, or give you something to turn over in your mind when the house is quiet and you can't sleep. It joins you to everyone else who has ever wondered what lies beyond the next horizon. So thank you for caring enough to follow this story all the way through, for letting your attention rest on a world you will never visit. That curiosity you're exercising is one of the best things about our species. It's the engine behind all our knowledge and much of our progress. Right now, as you listen, the largest planet we've ever found is circling its star. It doesn't know you exist. It doesn't care. But the universe is arranged in such a way that a being on a small rock, thousands of light years away, can figure out that it is there, measure its size, and speculate about its weather. That simple fact, that the universe can be understood, is quietly astonishing. The planet has been there for billions of years already. It was burning in its tight orbit, long before Earth formed from dust. It will likely keep circling, long after our civilization has come and gone. It doesn't mark time the way we do. Ages mean nothing to it. It simply follows the laws of physics. In our brief window, we have managed to notice it. We've given it a name in our catalogues, weighed it, measured it, argued about its interior, and woven it into our story of how planets form and evolve. That act of adding it to human knowledge is small on a cosmic scale, but big on a human one. The stars will still be there tomorrow night, and the night after that, waiting whenever you need a reminder that the universe is vast, strange and beautiful beyond anything we grew up imagining. And somewhere in Hercules, just another point of light to your eyes, is a star with a planet so large and so light that it could float. One more quiet wonder, waiting for whoever chooses to look.